And some of you who missed last Friday, I did not really go through quickly. Intentionally, I didn't go through quickly, because if you miss it, first few pages, then I'm afraid you will miss all the contents forever. Not only the Friday content, upcoming content, and I really want you to pay good attention. Otherwise, when you derive a certain equation, set portions of it, it's very easy to get lost. And to solve the problem, if you don't acquaint with some detail, then it's a little bit tough. So I want you to concentrate for a while. Then once you pick up the themes, then it would be very good. The theme we are working on is what? Input excitation and output response, the relation with the equation sets, how to handle that. So that's about all, okay? And RXX, RXY, SXX, SXY, you all know that. So we really learned all the definition, what that is, and the Fourier transform and Fourier transform pair, and all the definitions are done. So now we try to express the output response, like Y is output, X is input. So then in spectral form, how we derive that, what that means physically, vice versa, then how to eventually apply that in the engineering problem, so on. So pay attention a little bit. I was still slow, okay? And today I'm going to up to page 2. So it's just a few pages, total 3 pages. What I demand you to study pretty well, okay? And this is again I covered last couple of lectures, and if you look at carefully, it just repeat. Okay, repeat with a different wording. So that's what I'm going to do really today. And I'm going to, this is really equation after equation with a meaning in it. So what's SYY? Anybody can tell the name? What's SYY? If you want to say something. By the way, I have to tell you this. I carry the midterm exam graded, carry a couple lecture time here, but most of you were not here. So after that, I gave it to Higyu to just walk down to your office and give the solutions and all that. But if you didn't get your the midterm exam report, talk to Higyu, would you? But one common things you missed was problem number 2. 8 out of 9 missed it, except Yongbin. Yongbin is the only one who was able to solve. How long it takes to solve the problem? You have nothing to write. You can think, then just write the answer. That's simple. So it's not a tricky problem, but I really wanted to check out the meaning of the conditional probability. That's about all. Using the two dice, throw the two dice, then what's the probability that the sum of the numbers of two dice become 7, right? Given, that's a conditional probability. Given, what was the condition? Anybody remember? Given, sum is odd, right? That's a given. So what's the sample space? When you think about the addition of the two numbers, of course at the top side, what's the sample space? What would be the older combination for two numbers? How many chances? Can you tell? Each die has 1 through 6, right? So two dice. So you could have like 1, 1. I don't have to write anything. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. This is kind of the one way. Another way is you can just use the relation for conditional probability. That's another simple way. But logically, you can think, okay, how many such a combination of number you can have? That's called a sample space. How many? How many chances? How many? 36, right? No? Total is 36, right? No? So, sample space, 1, 1, 1, 2, 1, 6, and you can have a 2, 1, 2, 2, 2, 6, and you can have 6, 1, 6, 2, 6, 6. Sample is called a sample space. Total number of combination of two numbers. So it's just 36, okay? And sample space is 36. And given, how many odd and how many even? How many odd? How many odd here? If you have this is odd, this is an even number. Among the 36, how many are odd? Joan, how many? 18, right? Given is a conditional. Is when you look at my note, is for the joint probability density function, it's a volume, right? X-axis, Y-axis, vertical is probability, right? Density. So given means slice, right? And odd is 36, even is, odd is 18, and even is 18. Given the odd, which means 18, within the 18. Then how many among the 36, how many are there to get 36, to get 7? How many will become 7? This is a 5, 2. If you look at along the diagonal, I'm going to just draw diagonal like this. How many are there? How many are there? Among the 36, only 6. 6 are, 6 1 is odd, right? Then that becomes 7. This is 7. Here, 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 here. So among the 36, how many are 7, which is odd, of course, which is 6. Among the 16, there are 6. It's 1/3 of the probability. So straight. Other approach, you can do the set the probability dense, the probability that the sample space is A, and odd sample space as B, and you can get the AB, that's conditional probability. If you look at, you took the probability course. I bet most of you took the probability course, right? Tammy, you took the course? So this is within 10 pages of probability, the course. This is like A, and this is a B event, right? So this area, what do you call that? AB, intersection area. So you're looking for the probability of intersection over the probability of odd means A or B, as you define. So I want you to look back the problem number 2, okay, using the equation set. Equation set means probability A over B is equal to probability B over probability AB. This kind of the equation set. So spend a little bit time that you can think. Then I think Choru and Juhung, right? I forgot all the time. Jusong, right? I asked you and Yongbin also last Friday to really work it out, right? So I want you all work it out, problem number 2, with the thinking, some thought. And any problems in me, you should really sit down and do that. But in the exam, you don't need to think. Just it takes a minute, not minute, couple seconds to get to 1/3. Nothing to write much. So that's what the others are. Looks like all good. And I hate to comment on the final exam. Maybe I'm going to put it out some problem in probability area. Very simple, straight. But this is really an intelligent problem. Doesn't take much time. But you can do or cannot do. Okay, this SYY is and SXX, what are they? Because I want to quickly review, because last 1 week, most of you are out. What's SYY? What spectra? Auto spectra of what? This is chapter 4. Auto spectra, of course, YY, everybody knows is so. Auto spectra or power spectra of what? The midterm exam, I'm not that happy. Why? Because the range of, let me turn this off. Range of the score point is 24 to 42, which is not good. I really wanted around between 40-45. But highest score was 42, lowest was 24, which is not. It spread all the way across. So I want you to pay attention for next 1 month. SYY, Y is the response. So SYY is power spectra or auto spectra for output response, expressed using the input autospectra and the transfer function. So H is a transfer function, or you can call a frequency response function. Is H is a complex or real? Is H complex or real? H is, what do you call H? Frequency response function or simply transfer function. H is complex. It has a real part, it has imaginary part, or the magnitude and phase. So when you conduct experiment, I mentioned to you already a few times, this is something like a shaker, usually input. Input means excitation, applied excitation. And this transducer, usually I use a notation, summation sign for the transducer. This is output transducer. Of course, the wave propagation path would be like this. That's what I'm using it. When you excite the one point in the domain, like a plate, then you can pick out the response at different point. And the small h is called what? Small h is called? You decided not to talk, huh? What do you call small h? Unit impulse response function. So Monday last week I talked about the h, small h and capital H. These are the Fourier transform pair. Okay? So capital H is a Fourier transform of small h, impulse response function. What does it mean? Physically, what does it mean? Unit impulse response function. What that means? Shusong, what that means? Impulse response function. Say, simply speaking, and you're hit by the hammer, okay, it generates a response. That's what is called the unit impulse response function. Simple. And I said before, when you apply the impulse, we usually use delta function. Delta function, right at F0, what's the amplitude, what's the magnitude of amplitude right at the F0 for the delta function? For delta function, magnitude is magnitude of amplitude is, Yunseok, what is it? Infinite, right? Infinite. Delta function is infinite. What's the integration of delta function? What's integration of delta function? Right at F naught. What is it, Charu? Integration. 1 is a 1. Area is a 1. This is what we know. We use a delta function quite a bit. Okay. So when you have excitation, this is time t, impulse function, then you're going to have the response, which is called the h function, h tau, impulse. This is impulse response. It's a decaying, like due to the damping in the system. That's the meaning. Small h tau. Now, if you take a Fourier transform of unit impulse response, then you have frequency response function, of course, which is in frequency domain. So that's what we cover. We cover in chapter 1, I think, or chapter 2. Then I covered, I think, last week. So that's where we are. And SYY is output response power spectral function here. And I put a box around, which is kind of important to remember or to be able to derive. So capital letter Y and H and X is all Fourier transform of Y, small h, and small x, okay? Fourier transform. So this is the approach I really derive this kind of the expression. So Y star is not convolution here. Star here is conjugate. So two things with star, sometimes conjugate, meaning the conjugate, but sometimes convolve. X star Y, X converved to Y. I think I talked to you just before I start to talk chapter 4. And Y is equal to H X simply, okay, in frequency domain. Then Y star, if you take a conjugate, Y star, H star, and X star is all frequency domain. Then Y star, you can really switch it. It's commutative, the law is valid here. And this, you see, this is also wrong here. Anybody can spot the wrong expression here? This is all the PowerPoint file. What's wrong here? Y star is equal to, you don't have this, is H star and X star. This is what just to take the conjugate from this equation, then you shouldn't have this. I'll get the corrected one, and I'll throw this away. And H star and X star. Then Y and Y star, or you can say Y star Y is really same thing, is equal to, you have that, that's correct. H times H star, or H star times H is equal to H absolute square. If has a problem, let me know. So, but this is like this is like an expression we're always using it. Assume T is really infinite. T approaches capital T, duration of the data to be taken for processing. But usually we are living in a finite world. Everything is finite. So assuming here, just reminding that capital T exists in reality. It's called the finite, the spectra via finite Fourier transform. So K is here. What's a K here? I better start asking you a question rather than I keep talking. This is like an outcome event. This is an event. So you take the finite, the sample time record, then after n you have another time record, another time record. Then each record, so up to certain number of records. So K is one of the sample record. So K is sample record. Right? Sample record. So if your K was infinity, then you call the theoretical expression for the spectra and all that. So it's a kth sample record. Eventually you can express as H times K, the X. K goes to 1, 2, 3, all the way to the infinity. Showing the T here, this means finite, okay? When I drop this, then that's a theoretical expression as shown up here. Star, correct expression. Then YK star multiplied by YK, this is all the frequency domain. X star, YK star, YK. So this could also, this guy and that guy associate together. And this guy, H times XK associate together. Because Y is equal to H, X in frequency domain. So once you have that relation, then spectrums is very easy to express all the time. So back to the definition over and over again. SYY is output response, the auto spectra density function. Definition limit T goes to infinity. This is expected mean value of, and YK star and YK. Then yk, you have expression right here. X multiplied by, h multiplied by h star is h squared. Make sense? Anything not comfortable, you have to let me stop and digest and move on. This is the way you will never forget for derivation. Don't do it, just by your brain. Okay, this will be this, this will be that, then you will confuse. So this is a good way of doing it. So this is just a rewrite to make sure. And now, two items. One is SYY, and the other one is SXY. What do you call SXY? Cross spectra. Okay? Cross spectra is expressed as HSXX. This is input excitation, auto spectra or power spectra. Power spectra is rear. SXY is rear. Yes or no? SXY, I said, is rear. Right or wrong? Jebam. 50% chance to win. SXY is cross spectra. Cross spectra is complex, right? We did all this in chapter 3. I just make a connection. What's the X here? What's the Y here? X is input excitation for mechanics problem. Y is output response. That's about all. Then I express output response using the input excitation. That's about all. Remember, SXY, I'm not asking you to memorize it. We have done all this derivation, and how to derive this using the similar idea. X is X, input excitation. The Y is capital Y is equal to something times something. What are the something? H times X. So XY, capital X, capital Y, is equal to the X times H times the X, isn't it? So always think about the first the time domain, throw into the frequency domain, then express in spectra. XXY is this. Remember, T approaches to infinity, then capital T drops off. The delta 1 is finite, the delta function. If I set the small width of the strip, vertical strip, very small width, then delta 1 goes to the delta. Delta 1 is a finite delta. I'll just talk. Finite amplitude of the delta function. If I set the width very, very small, then the amplitude of the delta function, delta 1, becomes infinity. So you call the delta function. That's what the definitions you are using it, right? So T goes to the infinity, then you can drop this t here, f and f. This is xk, kth the sample record, star times h, the k is sxy. Then replace the yk as the input excitation in frequency domain. Then you can tell y is equal to h times x. Whoever working on the control, there are a lot of similar notations you can tell. So over here, x star, y is h, x. Then expected value of this is h is a constant. That's a system dependent. H and small h is a constant, system dependent. So you can take outside of E, so I put it outside here. Then you have x star, then x. This is in frequency domain. That's what the SXX is. So you have that equation, that two equations really, really important. SYY at frequency domain is HF square. This is one equation. It's a rear. This is a rear. This is a rear. SXY cross spectra is equal to H SXXF. This is complex, complex, and the rear. These two equations is really beginning of spectral analysis. And delta 1 when width, this is like has this width, I'm going to say epsilon, this is time. If this could be a F frequency here, doesn't matter, frequency or time. This, when epsilon goes to 0, this goes to like F. This is a delta function. This is called the finite delta function. Okay. So that two equations, this is really beginning. This is really no difference than a previous page, but look at the spectral function with a different close on it. So that's about all. So here, what I did here, just to take, this is a complex function. Complex function means it has a real part and imaginary part. Or in engineering sense, the magnitude and phase is more meaningful. So that's what I'm doing it here. So SXY without the absolute sign, SXY is equal to HF times SXX. If I use, this is a two-sided spectra, right? From minus infinity to infinity. But if you, in reality, the frequency, negative frequency, doesn't mean anything in mechanics sense. So you assume F is always greater than 0 or equal to 0. Equal to 0 means what? That's a statics problem. Like mean value. Frequency of the mean value is equal to? Frequency of mean value is equal to 0. When you express spectral function, when you express a spectral function for something like, could be like this, and you can compute this is some signal x, this is t. This could be, you can easily calculate the mean value, mean of, let's say, x. Then you throw this into the frequency domain. Okay, then frequency domain, magnitude-wise. So this is f. And for this, could it be, for example, could it be like this? Okay, spectral values. Compute a certain delta f frequency. You compute the amplitude, just to plot that and connect to that. Then where do you put the mean value here? It has a mean. Where do you put the mean? Mean has what frequency? 0 frequency. So right here, this mean value, you should put the amplitude right here at f is equal to 0, whatever the mean value is. So in the dynamic analysis or for dynamic testing, what's the best way to eliminate the mean value? How? How do you eliminate the mean value? You can easily manipulate. I'm going to reset this as this guy is a t, and this guy is up there, and this is a 0. We know the mean value. Put it away, right? In the testing, for the shock testing, that's what I usually do. Shock testing, when you put like a pressure gauge in underwater, then the needle changes because it takes up the pressure, static pressure. As you put deeper, then the indicator, the needle, really moving positive, which means as the gauge drops below the really deeper in the water, then it measures the pressure, static pressure, not the dynamic pressure, static pressure. Then I reset the needle to 0 and record the static pressure. Then conduct explosion testing. Then it just to pick up all the variation of the pressure. Then what I have to do, I have to add the static pressure to get the total anytime. Okay, so that's what. So if you do this, then you have to compensate. So this guy, if it's a red color, this guy is. If I set this guy is at time t1, so this is x at time t1 plus mu x. But the measurement shows only the xt1, doesn't see the static pressure value. Okay, so this is another expression, simply speaking, and because of the complex quantity, I put the absolute, 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 absolute. But what happened to SXX? SXX is the autospectra which has only real part. Imaginary part not there. You remember? And I rewrite back to here. And H has real and complex. So then I just wrote the vector, the complex plane. So this is H absolute. Then this is the phi angle. HR is a projection into the x-axis, projection into the y-axis. That's what this is. HR, HI, you can express as absolute. This is called phase, right? Phase angle. PHASE, phase angle. SXX. Then this you can express as e to the minus j phi. Some people call phi, but I always call phi. Okay. It's another expression for the same thing of H absolute SXX. So this is complex H expressed as H absolute e to the minus j phi. Question. So please review, in addition to the Bandet's and Piazzo's book, if you want to, if it's not clear, still not clear, see me in my office. Okay? And make sure your note is, the lecture note is correct. This is old. Okay, I'll stop here, 152. So I'll see you Friday. And 3 from Changwon. Spend a little bit time on this, not much. I demand a review of my lectures and understand, and we'll do some exercise problems. Okay? Okay, I'll see you Friday.